Okay, so here we are. Remember, this is the Wiggers diagram, and Wiggers was just a person's name, Carl Wiggers. And so this Wiggers diagram was just an attempt to try to put everything that happens in one cardiac cycle on one picture, one view. And remember what a cardiac cycle is. It's a circle. So if we back up just one or a couple more, it's this. So this is a cardiac cycle. And remember, it happens over and over and over and over again. And if a person's heart rate is 75, which is just the average, yours may not be 75, but if it is, remember that each beat is going to take 0.8 seconds. And so the way you figure that out is you take the heart rate and you divide it into 60. And 0.8 seconds, you can see it right here on this thing. So here's 0.1 plus 0.3 plus 0.4, and we're back to 0.8. And then it's going to start over and happen again and again and again. So each part of this cycle is taking a certain amount of time. And if we put the ECG on here, right here's where we're going to start. And so that's the P wave. And remember, the P wave is all about atrial depolarization. And right behind the P wave, we're going to get atrial contraction. And so blood's going to get forced into the ventricles. And then right here is QRS. And QRS, remember, is two things. The atria are going to repolarize, so the atria are going to relax. But at the same time that the atria repolarize, the ventricles are going to depolarize. And right behind ventricular depolarization, we're going to get ventricular systole. So during this period of time, we have the atria relaxing, they're in diastole, and we have the ventricles contracting. So when the ventricles contract, remember, it's like squeezing a sponge full of water. The blood is going to get squeezed. It's going to try to go back this way, but the valves are going to close and prevent that. And then the pressure is going to get higher enough to open these valves, and the blood is going to exit the heart. And then here is the T wave right here. And right behind the T wave, the ventricles are going to go into diastole. Well, the atria are already in diastole. Remember, that started right here. So during this period of time, the entire heart is relaxed. The entire heart. And so this is sort of like a little pause between beats. And what it is the time that the heart fills up. It's the fill time. And you can see that happening here. Blood is flowing in from the veins, flowing in from the veins. It enters the atria. The atrial pressure is going to have these valves open, so it's going to go right on into the ventricle. And so this is filling up with blood, getting ready for the next beat. So we want to be able to see all of that in one picture. And so that's where this Wiggers diagram comes from. Again, that's just his name. But on one picture, we're going to be able to see blood pressure of the atria, blood pressure of the ventricle, and blood pressure of the aorta. Remember, we're only going to look at the left side. We're also going to see an ECG. We're also going to see where heart sounds take place. And we're also going to see ventricular volume. And so if you look at it, this is nothing but a timer. That's all it is. So we're going to start right here. And we're going to start right at the P wave. And so one cycle is going to last to the exact same point on the next ECG. So that's one cardiac cycle right there. And that one cardiac cycle, if your heart rate is 75, and we're going to divide it into 60, we're going to get 0.8 or 800 milliseconds. So what we see when we look at this is the timer and the ECG. Well, we have to remember what the ECG means. Remember, the P wave is atrial depolarization. And right behind atrial depolarization, we're going to get atrial systole. And then QRS, remember, is two things. QRS is the atria repolarizing. And right behind that, we're going to see atrial diastole. And the diastole is going to last all the way until this next P wave, and then the same thing's going to happen over here. And so if we look at the next slide, we see exactly that. So there's the P wave. Right behind it is atrial systole. There's QRS. Right behind it is atrial diastole. Until we get to the next P wave. Same thing, again and again and again. But remember, not only is the QRS atrial repolarization, it's also ventricular depolarization. And right behind depolarization, we're going to get ventricular systole. And so the ventricles are going to contract. And then we get to the T wave. And the T wave, remember, is ventricular repolarization. And right behind that, we're going to get ventricular relaxation, ventricular diastole. And so the next picture just shows exactly that. So there's QRS, ventricular systole. There's the T wave, ventricular diastole, until we get to the next one, and then it's going to start all over again. So far, that's what we see. Any questions about any of that? Nikitra, do you have any questions about any of that? Okay, so the next part of it is what it's going to show are pressures. And so we would expect pressure to go up during systole, because remember, that's squeezing, that's contracting. And we would expect pressure to go down during diastole, because that's relaxation. And that's exactly what we're going to see. So during atrial systole, we should see atrial pressure go up. During atrial diastole, we should see atrial pressure go down. During ventricular systole, we should see pressure go up. And during the ventricular diastole, we should see pressure go down. And look at these arrows. I drew these small, and I drew these large. Well, there's a reason for that, and that is because the thickness of the atria is thin. There's not much muscle. And if you can't have much muscle, you're not going to have much pressure. But down here, the walls are much thicker. And a thicker wall is going to give you more pressure. And don't forget, the left ventricle is thicker than the right one. And so it's going to have even more pressure. Well, so what we're going to see are pressures. And we're going to see atrial pressure. And we're going to see ventricular pressure. But we're also going to see the pressure in the large arteries. Large arteries are the aorta and the pulmonary trunk. Well, look, there are two atria, two ventricles, and if we look at the aorta and pulmonary trunk, that makes two more. So that would be 6 lines. And 6 lines is very busy. So instead of doing the whole heart, we do them separately. And this one is just the left side. So it's just going to be the left atrium, the left ventricle, and the aorta. We make a whole different Wigger's diagram for the right side, and we'll look at it a little bit later on. So that's what we're going to see next. So when we look at this, That's exactly what we see. Pressures. So look, pressure. So if we look at it, here's 0. That's no pressure. Look, as you go this way, pressure goes up. In other words, you're squeezing harder and harder and harder. And so if we look at the atrial pressure, remember they're very thin. It doesn't go up or down very much. It goes up during systole, and it goes down during diastole. Same thing with the ventricles, but they're much, much thicker. Here's the ventricle line. And look, it's going to go up during ventricular systole, and it's going to go down during ventricular diastole. So up, back down. And it's going to happen over and over and over. And then the third line is this one, which is the pressure in the aorta. So remember, the aorta is the large artery that comes off of the left ventricle. And so what happens is, as blood gets pushed into the aorta, the pressure is going to go up. So when the ventricle pushes blood into the aorta, it goes up. That's during ventricular systole. That's the squeezing. In other words, we're squeezing blood out of the ventricle, just like you squeeze water out of a sponge. And that blood goes into the aorta. And then when you relax, the pressure is going to begin to fall. Now, it never falls as low as it does with the ventricle. Remember, we said that the reason why is because of the walls of the aorta. They're like little rubber bands. And when you push blood into the aorta, the walls bulge out. It's like stretching a rubber band. Now, when you release a rubber band, here it is stretched, it goes back to its original length. And the same thing happens here. When the heart stops pumping, the walls of the aorta are going to squeeze back in because of these like rubber bands, these elastic connective tissue. And that is going to apply pressure to the blood. So that means there's going to be some pressure left. This is from those rubber bands. This is from that elastic connective tissue. Does that make sense to everyone? Any questions? Makitra, do you have any questions from that? Okay, one other thing we can see on here is when the lines cross. So look, those two lines cross right there. And again, they cross right there. And these two lines cross right there. And again, they cross right there. Well, what's happening is when the lines cross is the pressure is getting higher or lower than the one above it. So if I look at this part over here, look, the blue line is bigger than the red line. In other words, the pressure in the left atrium is higher. But look, right there and all the way this way, the red line is higher. And so now the pressure in the left ventricle is higher. Well, as soon as that happens, blood tries to go backwards. Remember, there's a valve right here, the left AV valve, the bicuspid valve, the mitral valve. And when that blood tries to go backwards, this valve closes. And that's exactly what happens right there. This valve closes. If I continue to follow the line up, look, over here, this whole area from here to here, the black line is higher than the red one. And when the pressure in the aorta is higher than it is in the ventricle, the valve is closed because blood's trying to go backwards. But when I get right there, look, now the red line is higher than the black one, and that's all the way from here to over here. So in other words, the pressure in here has gotten so high that this valve opens and blood is going to leave. But as soon as I get right here, it switches back again. So the blood that's in the aorta rushes back and closes this valve. And that's what happens right there. And then look, the pressure continues to fall. Well, from here to here, the red line is higher than the blue one, all the way from here to over here, but right there. Look, the red line goes below the blue line. When that happens, that means that the pressure in the atria is higher than it is in the ventricle. And once this valve is going to open back up again and blood's going to flow through. Any questions about the valves opening and closing? Okay, and then there's only one other thing on this Weir's diagram, and that's this. And what this is how much blood is in the left ventricle. In other words, not the pressure, not how much pressure, but actually how much blood, the volume. And we measure volume in milliliters, and that's exactly what it is. So look, I'm adding blood to the ventricle, so the ventricle's filling up. But here I'm squeezing it, just like squeezing a sponge in your fist, and I'm pushing the blood out. And here I'm letting the blood come back into the heart. So what's happening is the heart fills, the heart empties, and the heart fills back up again. Well, it fills during diastole, when the heart's relaxed. That's when it fills. It empties during systole, contraction. That's when it empties. And so we can see exactly that. So look, diastole, that's relaxed. So it's filling. Systole, that's contraction. So it's emptying. And then we're back to diastole again. So it fills back up again. And so when we look at this, there's 2 points that we need to pay attention to. One is this one. That's when the heart is as full as it's going to get. In other words, it's not going to get any fuller than that. It's as full as it's going to get during this beat. And there's a name for that. It's the end diastolic volume, or the EDV. And look at what that word means. Diastole means relaxation. So it's the volume at the end of relaxation. It happens right there at the end of diastole. And that's as full as the heart is going to get. And look, that heart has 130 milliliters in it. And that's as full as it's going to get, because we're going to start squeezing the blood. We're going to start squeezing. And as when we squeeze, we're going to push the blood out. It's going to go from the ventricle into the aorta. We're going to push it out. It's going to go this way. And so there's going to be less and less and less blood in it as there goes out. But we're going to keep pushing it all the way through systole. But as soon as systole ends, we stop squeezing it and the pressure goes down, and look, it doesn't get any emptier. So the other point here is right here. This is the end systolic volume, or the ESV. And if you look at what those words mean, look, it's the amount of blood at the very end of contraction. And that's as empty as the heart is going to get during this beat. So we have these 2 points, EDV and ESV. Well, if we subtract those two, we get the amount that came out, amount that exited the heart. And that has a name too. That's called stroke volume. So EDV minus ESV equals the stroke volume. Any questions about any of that? So that's this Wiggers diagram. And what I'd like you to be able to do is take this one and look at it. Think about where it is. There's P wave, QRS, there's T, there's systole, diastole. And if you can put that on there and put that on there, in other words, relate those two, it's much, much easier for you to understand everything. His stroke volume, how much blood is ejected? Exactly. That's how much blood was pushed out of the heart, out of the left ventricle during that beat. So if we look at it, we can figure it out. So remember the equation is just EDV minus ESV. So if we plug in those numbers, we should be able to figure out what stroke volume is. So EDV is 130, so 130. ESV is 50. So if we look at that, 80 milliliters of blood were ejected or pumped out during that beat. Now it changes. It's not the same every single beat. But during this beat, that's what it was. Make sense? Any questions? Okay, so that's kind of what we covered last time. We talked about some other things too. We talked about the valves closing, and we get the heart sounds. And remember, if you want to see where the heart sounds are, it's where the lines cross. And so we're going to get a heart sound here. We're going to get a heart sound here. Those are the heart sounds. So the first sound is when the AV valves close. The second heart sound is when the SL valves close. Now you can also hear when the valves open, but you need very, very, very sensitive equipment in order to do that because they don't make much sound. And then finally, we also looked at the right side of the heart. So here's another Wiggers diagram. But this is for the right side. So it's for the right atrium, the right ventricle, and the pulmonary trunk or pulmonary artery. But the lines are exactly the same as what we talked about. So there's the atrial pressure right there, that one. There's ventricular pressure, and there is the pressure in the pulmonary artery. So if we were to try to compare those, here's left atrial pressure, there's left atrial pressure. Here's left ventricle pressure, and there's right ventricle pressure. And then there's the aortic pressure, and there's the pulmonary artery pressure. Well, look, over here, they're all bigger. Every single one of those lines is higher, it's bigger. And that's because the left side is thicker. The right side, everything's much lower. And that's because the right side is much thinner. There is one thing, though, that's exactly the same on both sides, and that's this. Can our lab instructor make a video rotating the heart model? We don't have access to any of the models. We can't get on campus, and so I would say the answer to that is no. I'm really sorry, but right now we have no access, just like you have no access. I wanted to try to go one day and take pictures and do a video, and they refused. So the only people who are allowed on campus right now are the police and a few of the administrators. None of the instructors are allowed on campus. Okay, back to what I was saying though. There is one thing that's exactly the same, and that's this. And so remember what it is when it says full? What is that point right there called? Anybody remember? EDV, that's right. And remember what it is when it says empties it's going to get? What is that point called? ESV. Well, EDV and ESV is the same. EDV over here, EDV over there is the same. ESV over here and ESV over here are the same. And so remember, if I subtract those two, I get a stroke volume. I subtract these two, I get a stroke volume. The stroke volume on the two sides of the heart is equal, and it must be equal. They must be equal. The two sides pump identical amounts of blood. Now they're pumped at different pressures, but the volumes are the same. The stroke volume on one side must equal the stroke volume on the other side. Otherwise, remember, you get a disease called congestive heart failure. That's about where we ended up. So, any questions about any of that? Hopefully that's a little bit of a review, but remember you can always go back and watch the collaborates from the previous time, and so you can always like hear the full lecture if you want to. Okay, so let's look at what we're going to talk about today. We don't have very much left before the end of the exam. So think about this. The heart is pumping. Well, why is the heart pumping anyway? Why do we even have a heart? It's to make blood move. It's to circulate blood. And so we need that blood to circulate. We need it to come back because remember, we're delivering oxygen and then we're dropping off oxygen, picking up carbon dioxide. We're dropping off nutrients for picking up waste. We need this blood to circulate. And so we need some way of figuring out how much blood is circulating, and that is this. It's called cardiac output. So what cardiac output is the amount of blood that's pumped by a ventricle every minute. In other words, how much blood comes out of the heart every single minute. Well, we already know how much blood comes out with each beat. That's the stroke volume. Everybody remember that? Well, if we want to figure out how much comes in 1 minute, all we need to know is how many times does the heart beat every minute. So if we multiply those two things, we can get the amount of blood that the heart is pumping every minute. And again, that's cardiac output. So if we want to figure out cardiac output, it's really easy to do. All we do is we take heart rate and multiply it times stroke volume. So remember, an average heart rate is about 75. We saw that stroke volume over there at about 80. Everybody remember that? So if we want to know the cardiac output of that person, that Wiggers diagram, we would just multiply those two. And if I take and I do multiply 75 times 80, I get 6,000. So in other words, that particular person at that particular time, their heart was pumping 6,000 milliliters per minute. Does that make sense to everyone? Is stroke volume the average milliliter per beat? Well, you can only do it at a specific time. So you can take, say, 1 minute, 2 minutes, 5 minutes, whatever. But you can only do it for a certain amount of time. So when you say at a specific time, it may not, it's probably not 1 beat because we're talking about a minute, right? So this stroke volume is the average milliliter per beat during that time. Now, most of the time it's going to stay pretty much the same unless you're going up and down and exercising and doing stuff like that, and then it's going to change constantly. But it's at a particular time. So when we talk about it in general, we just talk about it like an average. But does everybody understand how to calculate it? So, heart rate, what's an average heart rate? 75. Again, remember that's across all people, all ages, genders, everything like that. And then at rest, an average stroke volume, that person that we saw in your diagram was 80, but it's actually about 75 also. So the two numbers pretty much are the same, which makes it easy to remember. So 75 times 75 is about this. Now, you don't have to remember that number. You can always calculate it if you need to, but that's what it is. And so what most people say when they say that an average cardiac output is somewhere around 5 liters. So those numbers are pretty easy to remember. 75 heart rate, 75 stroke volume, and sort of just an average cardiac output, 5 liters. Make sense? The other thing is, most people only have about 5 liters of blood. That's the average amount of blood that a person has. What that means then is if I'm pumping 5 liters per minute as a cardiac output, that means that every single drop of blood, the entire blood volume, is making the complete circuit. It's going from the heart to the lungs, back to the heart, out to your tissues, back to the heart. Every single minute. And that is at rest. So if you start exercising, cardiac output is going to go up because heart rate is going to go up. The heart's going to squeeze hard, so stroke volume is going to go up. So cardiac output is going to go up. And so it's not going to be making this just one time. It might be making it 2 times or 3 times. A trained athlete, like a marathon runner or someone, can make this circuit about 7 times when they're exercising at max. 7 times. That means their heart is pumping 5 times 7 times. In other words, it's pumping 35 liters of blood per minute, which is pretty amazing if you think about it. Make sense? Any questions? That is a lot. Now, that's not me. That's probably not you either. You know, that's someone who's in the tip-top shape and they're working at 100% capacity. But even someone who's not a trained athlete, cardiac output goes up. So the reason it goes up, excuse me, is because we're going to need more blood. You start exercising, you need more oxygen. You need more nutrients. You need to get rid of more waste products and more carbon dioxide. And the only way to do that is to make the blood flow faster. We're going to have to increase the flow of blood. We're going to have to increase the amount of blood that's moving through the circulatory system. Well, we don't want to do it just willy-nilly. And so we need to be able to figure out how much we need, when we need it, and how much it needs to go up or down. And so cardiac output is regulated. So let's look at cardiac output. Do you remember what the equation is? Somebody tell me what the equation for cardiac output. Cardiac output equals what? Heart rate times stroke volume. Exactly. So if I want to change cardiac output, the only thing I can change is either heart rate or stroke volume. The only way to change cardiac output is to change heart rate or stroke volume. So if I want to increase cardiac output, the only way to do it is to increase heart rate or increase stroke volume, or you could do both. That's the only way to do it because that's all that's in the equation. Heart rate and stroke volume. So think about what happens if I increase heart rate. If I increase heart rate, if I increase heart rate, what's going to happen to stroke volume? Remember the equation, cardiac output equals heart rate times stroke volume. So if this number goes up, that number is going to go up. Same thing with stroke volume. If I increase stroke volume, if this number goes up, that's going to go up. And if I increase both of them, that's going to go up a lot. Does that make sense to everyone? So, how do I change cardiac output? I change it by changing heart rate or stroke volume or both. So let's see how we do that. Let's look at heart rate. So heart rate, remember, is the number of beats per minute. That's all it is. How many times we're going through that Wigger's diagram, that cycle, number of beats per minute. So that means with every single beat, remember we're going to have an ECG. So here's a slow heart rate. We're going to speed that up. Oh, we're going to look like this, sort of. I'm not good at drawing this with a mouse, but anyway. So look, that one's beating just 2 in my picture. That's beating 3. So this is a much faster heart rate than that one is. But look what changes when you change heart rate. This ECG does not change hardly at all. What changes is this, the fill time. When we looked at this, we said that it's like a pie chart, and one of it is atrial systole, 0.3 is ventricular systole, and then this right here is 0.4. But when you speed up the heart rate, this is the part that changes. It goes down. Well, how are we going to do that? We do it two different ways. We can do it with the nervous system, and we can also do it with the endocrine system. Remember, those are our two regulatory systems in the body. So let's look at the nervous system first. There are nerves that go to the heart. Look, two different sets of nerves that go to the heart. One of them is sympathetic, and one of them's parasympathetic. So if we look at it, and we remember what sympathetic and parasympathetic are all about, we can tell what's going on in the heart. Remember, parasympathetic is rest and digest. Everybody remember that from A&P1? Rest and digest. So what does that mean? You're resting. That means you're taking a break, you're relaxing, you're sleeping, you're doing something like that. So what do you think happens to your heart rate when you rest? Does it go up or go down? That's exactly right. So this nerve is a parasympathetic nerve. And look where it goes. It goes to the SA node and to the AV node. Remember, it's called the vagus nerve. That's cranial nerve number 10. That is a parasympathetic nerve. And what it does is it slows the heart rate. So you're not exercising. Let's say you're watching TV, or I don't know, you're reading a book, or you're taking a snack, or whatever you're doing. This parasympathetic nervous system from the brain, the medulla, is going to send the signal to the heart, and it's going to tell the heart to slow down. Does it make sense? So how does it tell the SA node and the AV node to relax so that you wind up looking like this guy? Think about what his heart rate is. It's slow. How do we do that? Because remember, the heart is automatic. It's got those two properties, automatic, automaticity, and also autorhythmic, rhythmicity. Everybody remember those two properties? So how is the system going to make it slow down? Well, this is the way it works. So here is a normal heart right here. And look, it's automatic. You don't see any kind of stimulus. Automatically, it goes from here to I reach threshold, and then I get an action potential, and it goes back down. Look where it starts. It starts about minus 60. So look, it takes this much time to reach threshold. And look, it came back down to minus 60. So it's going to take exactly the same amount of time to reach threshold. It came back to minus 60. It's going to take exactly the same amount of time to reach threshold. So look, if I add this time and this time and this time, they're exactly the same. I'm going to get this very regular beat. And because it takes this much time to reach threshold, I'm going to have a heart rate of 75. Does it make sense? Again, it has to do with how much time it takes to reach threshold. Look, it's exactly the same every time. And I don't know what that time is, but let's say it's 2. So look, 2, 2, 2, 2, 2. When I add all those 2's plus the amount of time that it takes to beat, that's where I get the time And that's where I get 75 beats per minute. But what if it took less time to reach threshold? Or what if it took longer amount of time to reach threshold? The heart rate would no longer be 75. So look what happens. Here is the vagus nerve. And if I activate the vagus nerve, here's what it does. Look, it changes this. It's not that anymore. Look where it is now. It's here. So is it going to take a shorter amount of time or a longer amount of time to reach threshold? I'm not at 60. I'm like at minus 65. So is it going to take longer or shorter? It's going to take longer. Look, it's going to take this much time. Not this much time. This much time. And because it takes longer to reach threshold, I'm going to have a longer amount of time between beats. When I have a longer amount of time between beats, then the heart rate's going to slow. So this heart rate was 75, but when I send an action potential down the vagus nerve, it's going to drop this resting potential down, and my heart rate's going to slow to 40. Does that make sense? But we also, though, have another nerve that comes from the heart. This is the sympathetic nerve. It's a sympathetic nerve. And remember, sympathetic is all about fight or flight. So fight or flight. In other words, you're trying to get away from something or you're trying to defend yourself from something. You look like these guys. So look, both of these, their heart's going to start pumping like crazy because one of them is attacking and the other one's getting ready to run away. So during periods of stress or anxiety or excitement or exercise, we're going to activate the sympathetic nervous system. And what the sympathetic nervous system does is exactly the opposite. So I'm going to send an action potential on a sympathetic nerve. Well, look where it goes. It goes to the SA node and the AV node. This one also goes to muscle cells. So it has an effect on SA node, AV node, but it also has a direct effect on the cardiac muscle cells. Well, if we look at heart rate, this is what happens. So here was our original resting potential. There was when we activated parasympathetic. Remember, we moved it this way, so it took longer to reach threshold. Well, with the sympathetic, though, we move it this way. Look, it's not minus 60. I don't know what it is. It might be minus 50. But look how long it takes to reach threshold. Just that amount of time. So it reaches threshold much, much, much faster. And so if it reaches threshold much faster, we're going to have more beats. And so heart rate is going to go up. So heart rate here was 75. Heart rate here was 40. Heart rate here, look, it's 120. So what did we change? We did not change threshold. Threshold stayed exactly the same. What we're changing is resting potential. What we're changing is resting potential. So we look at this one. What is resting potential? You can look at it and see it. It's minus what? 60. And so I don't know how much time it takes to reach minus 40, but it takes that much time. But I look at this one, it's not minus 60. Look, it's minus 70. And so it's going to take that much time to reach threshold. And if I look at this one, look, it's not minus 60, it's minus 50. And so it only takes that much time to reach threshold. So it works by changing the resting potential of the heart. So you move the resting potential toward threshold. It takes less time. So we're going to have more action potentials, faster heart rate. And that's what the sympathetic does. On the other hand, if you lower the resting potential further away from threshold, it's going to take more time to reach threshold. So we're going to have fewer action potentials and a slower heart rate. And that's what the parasympathetic does. Any questions about it? Does it make sense? Yes, no? I don't care. Again, so you should be able to look at these and tell what's going on. So heart rate 75. Remember, that's just average. What is this person doing? They're resting. Look at this one, though. Heart rate is 40. This person might be sleeping or might be, I don't know, very meditating or something like that. Something very calming. They're certainly not exercising. If you look at this person, they're either excited or they're anxious or they're afraid or maybe they're exercising. Any questions about any of that? So that's how the nervous system affects heart rate. Let's look at stroke volume. Remember, stroke volume is the other way to change cardiac output because, again, cardiac output equals heart rate times stroke volume. Remember what stroke volume is? We calculated stroke volume. What is stroke volume? How do you calculate it? What is it equal? Where do we even get this number? Yeah, exactly. EDV minus ESV. So if we're going to change stroke volume, we have to change one of these or both of these. That's the only way to do it because that's what's in the equation. So if we want to change stroke volume, we have to think about either the amount of blood in the heart before the beat, the EDV, or how hard this heart is squeezed and how much is left in the heart when it's over. That's the ESV to get this stroke volume. EDV minus ESV. So what is this person's stroke volume? What is their EDV? Looks like 65. What is their ESV? Looks like 40. So what is their stroke volume? 25. But look, what if I had started with a bigger number here? So it's not 65. I started with 80. I'm not going to change the other one, but is stroke volume still going to be 25? Now it's 80 minus 40. What would stroke volume be? It would be 40. But look, I'm not going to change EDV. I'm going to change ESV. Instead of it going down to here, I'm going to make it down to here. So look, all that came out. There's only 20 left in there. So look, I didn't change this number at all, but I changed this number. So what used to be 65 65 minus whatever it was is now 65 minus 20. So what is stroke volume? So look, you can change either one of these and you can change stroke volume, or you could change both. So when we look at stroke volume, we have to think about the equation for it and have to remember that there's two things associated with it, EDV and ESV. Make sense to everyone? So that's the equation for stroke volume. And so let's look at how we're going to change these. Remember here, there's EDV, there's ESV, and there's stroke volume. We calculated this before, but what is this person's stroke volume at this time? So 130 minus what? 50, so it's 80. But what if this number had been bigger? Or what if this number had been smaller? That would have changed stroke volume. Can EDV be less than ESV? The answer to that is no. Let's go back to our picture here. If I only had 10 in this thing, the maximum I could pour out would be 10, right? If I pour out any of it, is it going to be 40? I only started with 10. I started with this much. And then I pour out some, is what's ESV. So look, I started with this much. This is what I poured out. That's the stroke volume. So the answer to that is no, it can never be less. But again, what if this number were up there? And then it goes down. Stroke volume would go up. But what if this number came down here? Stroke volume would go up. If I affect either one of these, this one or this one, I'm going to affect stroke volume. Does that make sense to everyone? So let's look at what can affect stroke volume. There are really three things. Don't forget, they either have to affect one or the other of these, or maybe both. But there's three things that affect stroke volume. One is called preload. One is called afterload. And one is called contractility. Well, I think the easiest way to visualize these is to think of this. Use this picture right here. Look, this is a guy on a bicycle, and he's pedaling. He's going across a bumpy road, and there's wind blowing at his back. How fast he goes is his stroke volume. So look, all three of these things can affect how fast he goes. So let's look at this. Preload, back up. Preload is the amount of the blood that's in the ventricle before it contracts. So look, there's more blood available, and I can push out more blood. And if I use this, there's the blood in there. If I use this, preload is like the wind at his back. So the wind at his back, the wind is pushing him. So is that going to make him go faster or slower? So is that going to make stroke volume go up or go down? That's exactly right. Preload, the more blood there is in the heart, the more you can squeeze out, the bigger the stroke volume. So preload helps stroke volume. And preload is basically EDV. So the more blood I have in this little tube that we looked at, the more I can pour out. I have that much, look, I could pour a lot out. But if I only have this much, I can only pour out a little bit. So when you increase preload, you increase stroke volume because you increase EDV. Make sense? Afterload. So afterload is a little harder to understand. But think about this. In order for blood to get out of the heart, I've got to open these valves and I've got to push blood in here. Well, this is not empty. There's blood in there, and that blood pushes back. There's pressure in that, and that pressure pushes back. So in order to even get the valve open, I've got to have enough pressure here to open the valve so any blood can get back. It takes more work. It takes more work to push to get something pushing backwards. And so that means that the valve is going to be open less time. And if it's open less time, that means that less blood is going to get pushed out. Less blood is going to be ejected. And so what's going to happen is ESV, the amount of blood in the heart at the end of the beat, is going to go up. What's the equation for stroke volume? Stroke volume equals what? EDV minus ESV. So what happens if the number gets bigger? What happens to stroke volume? It goes down. Remember what our numbers were? 130 and 50. So we got 80. That came off our Wiggers diagram. What if it wasn't 50? What if it's 80? What would stroke volume have been? It would only been 50. So this afterload, if I increase afterload, what is that going to do to stroke volume? It's going to decrease stroke volume. And look, it's like this. So here's our guy. Again, he's on this bicycle and going, and afterload is like the bumpy road. Look, it's a bumpy road. You ever ridden a bike on a bumpy road? Do the bumps speed you up or slow you down? Do the bumps speed you up or slow you down? They slow you down. So in other words, if I make more bumps, if I increase afterload, what is that going to do to stroke volume? It's going to decrease stroke volume. And that's exactly what it does. So look, if I increase afterload, it's going to decrease stroke volume. Does it make sense? So remember, preload increases EDV. Afterload increases ESV. Don't forget, what's the equation? It's EDV minus ESV. That's what stroke volume is. So if that number goes up, that's going to go up. But if that number goes up, this is going to go down. Make sense? And then there's one more thing, and that is contractility. In other words, contractility. Remember I told you to think of the heart like a sponge with water in it? And that sponge with water in it is in your hand. So here's a sponge, and you're going to squeeze it with your hand. So think about this. If you squeeze, if you look at the camera over here, if I squeeze gently, I'm not going to make much water come out of that sponge. But if I squeeze really hard, I'm going to make a lot come out of it. So if I take a sponge, I squeeze it, squeeze, squeeze, squeeze from all sides. Depending on if I squeeze gently, a little bit of water will come out. But if I squeeze really, really, really hard, a lot more water will come out. Does that make sense? So don't think of the sponge now, think of the heart. So here's the heart. If the heart squeezes gently, how much blood is going to get pushed out into those arteries? Not very much, just a little bit, just a little bit. But if I squeeze really, really, really hard, in other words, I contract very, very hard, a lot more blood gets pushed out. Well, that is like our guy pedaling. So pedaling is getting contractility. Just like when you pedal a bicycle, you're working like crazy. You're using a lot of energy, a lot of muscle, and so on. Well, when the heart contracts, it's the same way. So if this guy pedals harder and faster, what's that going to do to his speed? What's that going to do to stroke volume? It's going to make stroke volume go up. So if I look at it, contractility, if I increase contractility, it increases stroke volume. Does it make sense? So there are three things that affect stroke volume. And here are those three things: preload, afterload, and contractility. And again, I think the easiest way for most people to visualize this is to think about this picture right here. Just imagine it when you're taking a test. And just remember this guy on the bicycle. There's wind at his back, which helps him go faster. This bumpy road, which is going to slow him down. It's going to make him go less fast. And then he gets to choose how fast he pedals, how hard he pedals, and that's also going to change stroke volume. Any questions about it? So which of these three things do you think you have the most control over? Which of these three do you have the most control over? Back to this. Which of these three things do you have the most control over? Sure, contractility. He gets to choose how fast he's going to pedal. He doesn't have much control over the wind. Wind just comes. And he also doesn't have much control over the road, whether or not it's bumpy or smooth. Somebody else has control over that. And so the same thing is true here. They all affect stroke volume. All of them do. But the one we have the most control over is how hard we make the heart squeeze. And the way we make the heart squeeze harder has to do with the sympathetic nervous system and with hormones. So, trying to get back for so when we look at this, not only did this sympathetic nerve go to the SA node, and not only did it go to the AV node, that affects heart rate, but it also goes to these muscle cells. And what it does to those muscle cells is it makes them contract harder. It increases contractility. Not only does the nervous system have an effect, so does the endocrine system. So remember the endocrine system? We talked about the adrenal medulla. Remember the adrenal medulla releases epi and norepi. I should put that slide in there again. So increased sympathetic stimulus, also epi and norepi. And then there's also drugs, medicines that increase the amount of calcium in the muscle cells. So, think you can remember this? So, preload. What is preload on this picture? It's the wind at his back. What is afterload on this picture? It's the bumpy road. And what is contractility on this picture? It's how hard he pedals. So, preload. If I increase preload, what is that going to do to stroke volume? What's it going to do to stroke volume? Increase. What about if I increase afterload? What's it going to do to stroke volume? Decrease. And what happens if I end contractility? What's that going to do to stroke volume? It's going to increase. And of the three, remember which one I have the most control over? It's contractility. So this also shows that, and look, here's preload, increases stroke volume. Afterload, decreases stroke volume. Contractility, increases stroke volume. And then we already know about heart rate. Heart rate, if we increase it, stroke volume, if we increase it, we're going to increase cardiac output. So those are the things we can do to change cardiac output. We can increase heart rate. We can increase preload. We can increase contractility. Or we can decrease afterload. Does it make sense to everyone? And those are the only ways you can do it, because there's nothing else in that equation. So look, we had an equation. Let's back up. We had an equation for cardiac output. What was it? Cardiac output equals heart rate times stroke volume. But we also now have an equation for stroke volume. What was that? EDV minus ESV. That's right. So by substitution, we can put this in here. And so our real and true equation for cardiac output is heart rate times EDV minus ESV. That shows us everything that we can change to change cardiac output. So the real and true equation for cardiac output is heart rate times EDV minus ESV. So look at this equation. If I want this number to go up, I can make that number go up, that number go up, or that number go down. Does it make sense? We go back here. Remember, here's EDV. Here's ESV. So if I want this number to go up, I can make that go up or that go down. Again, there's EDV, there's ESV. This is also ESV. So, what's our equation for cardiac output? Cardiac output equals what? Heart rate times what? EDV minus ESV. So if you have your Wiggers diagram printed, you should flip it over and write this. This is the real new equation for cardiac output. And if you want to figure it out, or if you want to know what's going to affect cardiac output, the easiest way to do is to look at this equation. Okay, so look what happens with stroke volume. So here's a normal person, untrained person. And remember, this is at rest. So at rest, this is what their heart rate is, and this is what their stroke volume is. So there's their stroke volume. But look, if I take that same person and make them exercise at their maximum, so at their absolute hardest exercise they can exercise at, look what happens to stroke volume. It does go up, but it only went up that much. Because in an untrained person, the walls of the heart, just like any muscle, if you work it, it gets thicker. So the walls of the heart here are thin. And if they're thin, they cannot produce much pressure. And if you can't squeeze very hard, you can't push out very much blood. So stroke volume is going to be low. But look what happens very quickly when you start training. So here is a person that's in fairly good shape. Look what happened there. Their stroke volume at rest, this is at rest, goes up. Well, remember, heart rate times stroke volume is cardiac output. So look, if this number goes up, this number can go down. So if I were to compare the heart rate of this person versus the heart rate of this person probably has a higher resting heart rate. Probably isn't 75, it might be 85. But this person, it's going to drop because with every single beat, they're pushing out more blood. And it gets even more dramatic the more trained you become. So look, here's a highly trained person. Look, now with every single beat, their heart is pushing out that much blood, which means they don't need as big a heart rate either. It's going to go down some more. But even more dramatically, look what happens to the cardiac output when they're exercising. And then if you look at someone who's a very, very elite athlete, look at this number. With every single beat, that much blood is being pushed out. Remember I said that they could produce as much or have a cardiac output as high as 35 liters per minute? Well, this is why. Their heart is a much, much more efficient pump. Much, much more efficient. It pumps more blood with every single beat. Does that make sense to everyone? Well, there's an old saying, and it's pretty true, that we all get about 1 billion beats. In other words, your heart beats about 1 billion times, and then it's done. You're going to die after about 1 billion beats. It just wears itself out. Well, look, this person's probably has a heart rate of 85. This person probably has a heart rate of 45. So if we get 1 billion beats, who's going to use up their 1 billion beats faster? This person or this person? And so people who are couch potatoes, they're sedentary, besides having a lot of other problems, they just don't live as long because they use up their 1 billion beats much, much faster than someone who exercises. Any questions about that? And then the last thing is there are lots of things that affect cardiac output. Lots of things. Could be excitement, fright, anxiety, exercise, all kinds of things. But no matter what it is, it has to come down to heart rate, ESV, and EDV in order to affect cardiac output, because the equation for cardiac output is heart rate times EDV minus ESV, and there's nothing else in that equation. So every single thing that you look at over here has to affect either this or this or this. It all comes down through those things. Any questions? So that's the end of material for the first exam. So when the cardioacceleratory and vagus nerves are stimulated at the same time, does the heart rate have no effect? Well, the answer to that is no. And here's why. So remember, we have both of them coming down here. There's the vagus nerve. It comes here and here. And here's the cardioacceleratory nerve. It comes here and here. Well, remember parasympathetic nervous system, a rest and digest system. In other words, it's sort of like a housekeeping system. It's your day-to-day activities, day-to-day. It's kind of like housekeeping. But the sympathetic nervous system is an emergency system. It's kind of like the body's 911. So think about this. What if you were doing your day-to-day stuff in your own house? I don't know, you're washing dishes or vacuuming or whatever. And all of a sudden your house catches on fire. Do you think these two things are going to cancel each other out so that they're equal in terms of importance? If you're vacuuming and all of a sudden your fire alarm goes off, are you going to keep vacuuming? Probably not. So the answer to that is the emergency takes precedence. So if you were to do exactly what you say, which is stimulate both at the same time, the sympathetic and the parasympathetic, what would happen is the heart rate would go up. Because this one would take precedence. Does it make sense, Anita? Yes, no? Okay. So that is basically the end of that material. Anybody else have any other questions? So don't forget, these recordings are available. You can go back through them as many times as you want to when you're getting ready to study. But I have another class at 12:30, so I'm going to have to let you go. Thank you for being here today. I don't know about the quizzes yet. I haven't had a chance. My internet just got fixed. But I'll try to get it worked out and then I'll send out an email, Naomi. Okay. All right. Well, I'll see you tomorrow if you show up tomorrow. So I'm going to go ahead and stop recording now.